Hello, and thanks for stopping by. I'm Natalie, the development engineer here at Essentium. Essentium provides industrial 3D printing solutions that are disrupting traditional manufacturing processes by bringing product strength and production speed together at scale with a no-compromise engineering material set. Essentium manufactures and delivers innovative industrial 3D printers and materials, enabling the world's top manufacturers to bridge the gap between 3D printing and machining and embrace the future of additive manufacturing. We hope the following information will be helpful to you and encourage you to visit our website at essentium.com to learn more. The webinar will now begin.
All right, hello, and welcome to Essentium's live webinar. My name is Leslie Bush. I'm an applications engineer here at Essentium and will be your presenter today. Today's webinar is entitled Component Masking for PCB Conformal Coating. Today's webinar will be recorded for your future use, and we'll go ahead and begin to get started. All right, so in this webinar, we'll be covering the introduction to conformal coating and the process itself, considerations for component masking, material selection, and printing considerations with the selected materials, and two use cases, two customers of ours, Mercury Systems and TTM Technologies. Then we will conclude and wrap up with a Q&A session. Masking surface-mounted electrical components is a crucial part of printed circuit board manufacturing. During production, conformal coating is applied to the surface of a PCB or printed circuit board to protect its delicate components from moisture and environmental exposure that could lead to corrosion and component failure. I'm sure you've seen a lot of this kind of like blue-green patina on old electronics that can lead to corroded and broken metal mounts that connect in turn to the printed circuit board, leading to defaults and overall useless electronics. One issue in the industry, as electronics continue to get smaller and smaller, we're seeing an increasing need for these type of protective coatings to ensure the longevity of electronics in things just like smartphones, laptops, tablets, and what have you. The conformal coating is a polymeric film manually applied in thicknesses as small as 25 microns. However, to maintain electrical continuity, conformal coating can be applied to areas, conformal coating cannot be applied to areas such as pins, connectors, test sites, LEDs, and through holes. These areas are masked off either manually or with automatic procedures before the coating procedure. Typical masking materials include masking tapes and dots, low ESD polyimide tape, and temporary and permanent protective fluids and gels. Those permanent fluids and gels are then abrased off from the board and cleaned off before going further in the production process. And if you see the production overview, we have for PCB production, we have cleaning and priming of the surface in order to ensure there's no dust, there's no particulates on the printed circuit board before the coating is applied. Next, we have the masking procedure, where the surface mounted components that need to be preserved are masked off either using tape or liquid gels. Then there's the application of the conformal coating material that ensures longevity of the printed circuit board and ensuring that it keeps it safe from any type of environmental exposure. Next is the demasking and finishing procedure, where any of the excess masking material is removed or abrased off before going into drying and curing, and finally expecting of the final conformal coat before being moved on into the next stage of PCB development. As we go forward in the In this webinar, we encourage you to submit your questions through the chat feature, and we will address those during the Q&A time at the conclusion of this presentation. This webinar is being recorded and will be sent to attendees for future reference. So in order to drive home what exactly is going on during the PCB conformal coating procedure, I'm going to show you this video of automatic the automatic application of conformal coating. It's being lit up under UV light at this moment. You'd see this head mechanically moving in X, Y, and Z, or X and Y tool paths that were previously prepared and programmed for this particular circuit board. It's moving about and masking off any of the areas that we don't want coated with this conformal coating. If the improper area is coated, that could then actually completely affect and negate the performance of this printed circuit board. So it's very important that precise and accurate application of this masking material is applied during the process. Unfortunately, it is a very time-consuming process when done manually. And if you can imagine, each one of those areas that are being masked off would have to be done manually for low volume production. So there are opportunities to invite human error during this conformal coating procedure. So despite the availability of these automated selective conformal coating equipment, they're quite expensive, very expensive. Investing in expensive capital equipment like this may not be maybe cost prohibitive, and maybe not the most cost saving or productive method of applying conformal coating or masking off these areas for the coating procedure. For companies that specialize in small volume or mixed batch manufacturing, where you're printing small quantities of specialized equipment, electrical equipment for various customers, this may not be efficient because then you're constantly reprogramming each toolpath for each specific item, which in turn requires more specialized training for operators, hiring an operator to operate and maintain this expensive equipment, and so forth. In these cases, the practice of manually applying this conformal coating is still prevalent, but can lead to imprecise coding due to human error. So both the application and the masking process, if both of them are done manually, that can be very time consuming and not effective for quick turnarounds in PCB production. If we look at this photo, we can see the manual application of masking tape applied to a printed circuit board. In this case, it's being done by hand, and you can see in this next photo, it requires very precise folding over each surface mounted component to ensure that the conformal coating material isn't leaking in and actually touching any of the components. So you have to ensure that you have very delicately folded tape over these printed circuit board components, and also ensuring that they're the right height and the right depth, so that there's no leakage of conformal coating that will go underneath the mask taped off areas. So there are still a lot of areas to introduce, like improper coding application due to this manual taping. Definitely saying manual and application a lot, but yeah, that's part of the use case. So next, let's talk about electrostatic discharge. So one of the important things is to understand the environment that these printed circuit boards are being produced in, and how we can ensure their longevity and ensure that they don't break down during the process. And this breakdown can occur due to electrostatic discharge. So electrostatic discharge can occur when two electrically charged objects come into contact with each other, and then this charge is then rapidly transferred between the two objects. ESD generated from the human body can be upwards of several thousand volts. enough to permanently damage the components on PCBs, or in worst case scenarios, can actually ignite flammable atmospheres and so forth. One example that was given to me from one of my colleagues was back in the maybe it's like 70s and 80s and previous automotive generations before us. There weren't a lot of ESD protective protocols in car manufacturing. And so there are often cases where if there was enough electrostatic discharge or buildup when someone was pumping gas or opening their gas tank, it was enough to potentially spark a fire and cause the gasoline in the pump or in the car to ignite at gas stations. Thankfully, we've improved a lot over the years, and current generation vehicles have many like electrostatic precautions to allow these charges to dissipate and not to lead to flammable or harmful situations. So to summarize, so this phenomenon can be generated from the human body. Some of the, so say for example, in rubbing two objects together, any type of friction or low humidity environments can generate this type of electrostatic event. So the high voltage pulse would enter an electronic device that's touched, resulting in malfunction or destruction of the circuits inside. So in order to prevent this situation from happening, we will add ESD or dissipative precautions or materials into electronic device that suppress or remove ESD and bring it to ground. So for example, some of the actions due to triple charging or rubbing objects against each other, that friction can also generate kilovolts that are demonstrated in this, displayed in this diagram here. For example, walking on carpet. If you guys remember from science class back in the day, they'd have you guys either like rub your feet in the carpet or rub your head with a balloon in order to charge up a device. You can see that you can create quite a large charge from these everyday actions. So in order to have the most effective ESD environments or ESD safe environments, you have to consider every single touch point that the printed circuit board might come into contact with during production. So if a human is handling or a person is handling a printed circuit board, they might have a charge that will then in turn transfer over to the printed circuit board. If you're placing a PCB on the table, that might have some static charge in there that could also damage the PCB and so forth. And so humidity also affects the amount of charge and static in the air that could then in turn destroy a printed circuit board. So some of the ways that we counteract this phenomenon is to use ESD safe packaging material, conductive clothing for assembly workers or anyone who's in contact with these printed circuit boards, grounded wrist and heel straps for assembly workers, anti-static mats, and humidity control. So going into the ESD safe packaging material, so that will protect the interior circuits or ICs from exterior electric fields. This resistant material will dissipate the charges as heat. So in turn, they're being dissipated by the seal or the material around it and not actually coming into contact with the printed circuit board and the components itself. So also having dissipative properties and clothing and using wrist straps and anti-static mats also creates a nice ESD safe environment. So you can see the example further here. We have, this would be the ideal working environment for someone in the PCB manufacturing environment or facility. Some of the optional things would be like foot grounders, floor mats, and floor grounding cords in order to ensure like even the movement of your feet on the tile won't in turn generate some static charge that could damage the PCB. but definitely everything, especially like table mounted and everything attached to your hands, are absolutely crucial to ensure a good ESD safe environment, allowing all that charge to be dissipated. So this is where 3D printing opportunities come. In order to find a nice opportunity to 3D print with ESD safe materials that could then interact with the printed circuit board. If you look at this photo here, this is the comparison between the masked off areas that have like ESD safe tape or masking tape before conformal coating is applied. And above here, we have 3D printed boots, or like they're called like boots, or like just like masks, 3D print masks that are then used to close off and seal off the printed the components, allowing both ESD, like a nice tight ESD safe seal, but also preventing that conformal coating from leaking into the component and damaging potential damaging connections on the components. The next thing we're going to talk about is considerations for 3D printing these masking boots and material selection. What are some of the things that you want to take into consideration when you are creating these 3D printed boots, and what can Essentium's material portfolio offer you? So let's talk about the concept of complexity is free. So this is a term, or I guess a saying that's very prevalent within the 3D printing or additive manufacturing sphere. Additive manufacturing allows for nearly limitless design freedom, material selections, and shorter cycle times. Considerations for masking boot design include dimensional accuracy, rounded edges and corners, multiple walls and infill, and layer height. And so to talk further about what we mean by complexity is free, what's great about additive manufacturing is essentially you have limitless design options. If you can create a 3D model of whatever concept or whatever design that you're working with, in turn, you can then 3D print it. So there's no additional costs added to your production. If you change the design on the fly, you don't have to say rebuild and create a new mold or a new tool. All you're doing is making changes to a CAD file, to a 3D digital file on your computer. That's the only change you need to do. And then you could go quickly reproduce printable or executable G code that can then be read by the 3D printer and printed. So it's very easy and very fast to make complex geometric changes, to make complex geometric shapes on the computer, and then quickly execute them as fast as the next day, the same day, or the same hour. So if we look at this graph here, we can see as geometric complexity increases, the manufacturing costs per piece increases with when we're talking about conventional manufacturing, say injection molding, blow molding, and so forth. However, with additive manufacturing, if we look at that green horizontal line, there is no change in cost per price as we create a complex part. With injection molding, if you have a design with a lot of features, a lot of overhangs, you might need to have additional CAM actions and complexities added into your aluminum mold, which will then add production time and costs to the development of whatever part you're injection molding. However, that's not present within the additive manufacturing process. Okay, so let's talk about thermoplastics. Thermoplastics are the space that Essentium thrives in and currently produces. We produce a wide variety of 3D printed materials that are usable on many extrusion-based 3D printers. So you're not, with our material platform, you're not limited to using our HSC machines. You're open to using any 3D printing machine that accepts 1.75 and 2.85 millimeter filaments. If we look at this diagram on the left, we can see we have two main categories of thermoplastics, amorphous and semi-crystalline materials. So we have a wide variety of portfolios of materials in our portfolio, ranging from like a cost-effective commodity and engineering grade materials, all the way up to ultra performance materials that have very high strength, high durability, a high heat deflection, and so forth. The considerations we want to look to are finding which materials are ESD safe, are non-marring or non-marking. They won't rub off or produce any particulate that would get on the printed circuit board, and also are chemical resistant, especially if we want to use these for repeated cycles of conformal coating. We want to ensure that the boots that we're printing can be reusable. That'll be the best use of your time rather than having producing expensive single-use boots. It's great to have a reusable option. So if we're looking at the ESD control spectrum, we have three main categories: conductive materials that you're familiar with, such as metals, that are great at transferring electronic charge through that conductive material in order, say, like for different cords, chargers, what have you. Then we have, on the opposite side of the spectrum, we have insulating materials, thermoplastics that will in turn provide insulating features. The section that we want to look at is ESD dissipative materials. The spectrum here, usually around the E to the 2 and E to the 11th range. That is the ideal range that we're looking at when we're testing for dissipative properties in a material. We want to ensure that we're within that particular range, that there isn't conductive properties, and that there are no insulating properties for whatever is interacting with the printed circuit board. If we take a look, once again, we're going further and further, you guys. If we take a look at Essentium's material portfolio, we have it broken down into these 5 main categories: general purpose materials, flexibles, high temp materials, fiber reinforced, and ESD safe materials. So this zone is primarily what we want to choose from when we're working in the electronics industry. What's great about, see, like this TPU line, so these are both, they kind of have a dual purpose, or very versatile materials, because TPUs are flexibles, they're known as elastomers, but these materials, this particular line is also ESD safe. So not only are you getting flexible properties, but you're also getting dissipative properties that are ideal for interacting with PCB and ESD environments. And as you can see, we have a distinguishing letter Z at the very end to indicate all of our ESD or dissipative materials. We also have some anti-stat materials that offer different properties. So with our Essentium Z line of materials, these are filaments that have enriched with multi-walled carbon nanotubes surrounded by a core material. So for example, our flexible ESD materials, they're surrounded by a coat of carbon nanotubes, while the core material is still TPU. So you're still getting the core material properties, or the elastomeric properties of this material, while also ensuring that your target surface resistivity is achieved. So the surface resistance that we're looking for, it could be tuned during our production process. If you have a specific application where our material may not meet your needs, we could then tune it from 1e to the 2nd or 1e to the 12th ohms based on this carbon nanotube loading level. Ideally, what's also great about these materials is that they're non-marking. They do not leave any residual like black marks or low particulates, like carbon particulate, that then get on to the printed circuit board and could actually cause electrical issues and reduce performance in the printed circuit board. So these parts, these materials, these SMC materials, can also make parts that meet ANSI, ESD, S541 specifications for static dissipative materials. So if we take a look at the non-marking properties of this carbon nanotube material or coated material, it's great because say if you even took a piece of paper and like did some marking, you would not get any streaks on both paper or a printed circuit board. However, with competing materials, if we look at the section on the left, when rubbed off onto a piece of paper, you do see marking, almost like working with a crayon or piece of charcoal of sorts. So that's definitely a very unique and a rare instance or property for extrusion-based 3D printing materials. So the use cases I'll be talking about at the very end of this presentation use two of our elastomer Z materials, TPU 74DZ and TPU 95AZ. So talking about TPU 74DZ, it's a high durometer filament in our ESD portfolio. It has non-surface marring properties, which won't cause any electrical failures or issues. These are industrially proven safe materials for ESD sensitive applications. It's also a no warp replacement for ABS, which is excellent. ABS is a very common extrusion-based 3D printing material, but one of the downsides to it is it has the tendency to warp quite frequently when 3D printed. So you have to have a more like a it requires a bit more attention when printing. You want to ensure that you have uniform heat throughout your 3D printing environment or the build volume when you're printing ABS. And so sometimes if not enough uniform heat is applied to the part, if there's a lot of hot and a lot of cold zones on that part, it might have the tendency to warp off the print bed or warp in other sections during the printing process. So if you're looking for ABS alternative, TPU 74D, both in its ESD and non-ESD formulations, is a great option and replacement. This material also has temperature resistance up to 120 degrees Celsius. Applications for this material include, like I mentioned, ABS replacement, ESD replacement. The chemical resistance makes it great for multiple cycles of exposure to chemicals, ozone, and abrasive environments. It's also great, the elastomeric properties also allow cushioning for vibration dampening and also for impact rated structural components. So ESD safe it can also be used to hold and enclose. It could be used to hold and close electronics, like I mentioned before, and create ESD safe jigs and fixtures and snap fit connections. So you can find some of the ways that we test for the electrical properties in our TDS sheets, technical data sheets for all of our materials. You can find these located at our Essentium website. And so one of the ways that we test the surface resistance for our 3D printed components is for our 3D printed material, is by creating this three-sided cube like you see on the left. So there are 6 sides that we then take a surface resistance probe, touch the probe to each one of these sides, and then we can measure the resistance in ohms. For the TPU 74DZ testing, this was printed at 295 degrees Celsius at 100 millimeters a second. And so we can see for each face of this 3-sided cube results in a different printing orientation. So if we look at face 1, the tool path for this particular section is printed on the XY plane, whereas say surface number 4, that was printed in the YZ plane if we go from like front to back, up and down, that would be in the Z and Y directions. So each orientation actually can change the surface resistance for your part. So it's very crucial to take that in consideration when you're designing and orienting your part for printing. If we look at the left here, on the right here, excuse me, we have the measurement positions on the left and the resistance in ohms on the right, ranging from 1.44 e to the third ohms to 5.10 times e to the seventh ohms. The second material we'll talk about today is TPU 95AZ, and the surface resistance for this material would be would also be measured in the same fashion that we just described. So TPU 95AZ, so it's a medium durometer filament. So it's a bit more flexible than the 74D that we looked at previously. I think I have, here we go here. So if we look here, this is an example of like, the flexibility of the TPU materials. I believe this was printed in TPU 74DZ. So it's a bit more rigid than some of the other flexible materials. And this was actually used as a cover for an aerospace application. It provides an ESD safe cover, and also the flexibility makes it easier to slot in to tight and narrow spots, and conforms very, very snugly to whatever environment that you're working on. So TPU 95AZ is a medium durometer filament in our ESD line. It also has non-moderating properties, so it will not rub off onto any surfaces. It's also industry proven, like everything else in our line. It's a nice balance between high elongation with great impact strength and resistance. So once again, it's great for creating vibration isolation and dampening, holding and securing electronics for manufacturing. It's great for inserts and jigs and fixtures. So depending on like your use case, you might need a kind of more stable or less flexible material, or you might need a more flexible material. So since we're talking about materials, one of the really important things is to ensure that you have properly dried material. I cannot stress this enough. It's very important to ensure that you're printing with what we call dry material. Different thermoplastics absorb inherent moisture in the atmosphere faster than others. For example, nylon materials are quite well known for their moisture-loving properties. So they in turn do need more drying time than others. If we take a look at this diagram, so for example, PA5 or PA12 is a type of nylon. The max moisture content there is 1,000 ppm. You could still print it. So that's the ideal max moisture content. So if we're doing testing, we're about to start printing, or if we're about to start printing a part and we want to do a moisture test, we want to ensure that we're not exceeding those max moisture contents for the material that we're working with. For the TPU-A and TPU-D lines, we have some recommended drying temperatures. You can purchase a drying oven. Essentium also produces dry boxes that can allow you to both safely store and dry your materials in a low moisture environment. We also have recommended drying times and max moisture contents. All right, so now we're getting into the customer case studies. First, we'll start with our customer mercury systems. So background about Mercury Systems. They're a US company. They're an electronics manufacturer at the forefront of defense technology. They serve customers from government agencies to defense contractors to commercial aerospace businesses. Mercury's U.S. manufacturing operation, also known as USMO, they specialize in low volume, high mix operations that prioritize the rapid production and development of new products to their clientele. Their mission is to provide printed circuit board assemblies to businesses across the globe. Their challenges with conformal coating are very common and understandable throughout the electronics industry. Companies that might do, millions of similar circuit boards. It may make more similar circuit boards. It may make more sense to produce the same, to invest, I'm sorry, in an automated masking machine, like I demonstrated or showed you guys earlier in the procedure, earlier in the webinar. However, they're specializing in low run production. So the time it takes to reprogram a tool path and masking path for each particular specialized component is very time consuming. So for their uses, they want to find an alternative to masking each one of these specialized components by hand. So many of the manual masking products, like using tape or using gel that's applied through a squeeze bottle, they're single-use solutions. You have to peel it off and discard it. So it's tedious, it's slow and time-consuming, and it's not it's not always effective, especially when human error can be taken into account. So on the left is a snapshot of Mercury systems in the production process for TPU boots. So in order to solve their need, they purchased one of our machines and then used TPU 74DZ in order to rapidly produce masking boots. You can fill up the entire print bed with these boots because they're quite small. Depending on the components, you might see boots that might be a little bit longer or even smaller. So for their use case, 3D printing these masking boots costs roughly $500 in material time and labor time. In comparison, injection molding the equivalent boot designs cost Mercury Systems $9,000 in tooling and parts. 3D printing was able to reduce their production costs by 95%, which is really impressive. The lead time was also decreased by 85% because instead of waiting roughly 12 weeks, turnaround time to receive injection mold boots, they were able to design, test, and print them and iterate them in-house in the span of one day, really. So they're able to get into production the same day and printing full beds of TPU boots. The second use case we'll talk about is with our customer TTM Technologies, who also made masking boots, but with TPU 95AZ. So once again, we're in the same situation where we're trying to mask off the PCB assemblies during the conformal coating process. So these boots or caps, they're used to mask off the components that we don't want touched. However, specialized pre-existing silicone caps are in short supply, and you have to ensure that they actually fit each component snugly. So in turn, TTM will previously use masking tape. It requires the proper cutting, folding, and application of each taped bundle to the component to ensure a tight seal. So once again, this is a very time-consuming, manually laborious procedure. So to save on time, they partnered with our high-speed extrusion machine and printed TPU 95AZ boots. So to save on labor time, they were able to produce over 2,000 boots or masking caps for various connector sizes. So they chose, once again, an ESA-safe flexible material from our elastomer line, and it was able to completely eliminate the bottleneck of manually applied masking. And they also save time in the application procedure, saving more than 5 minutes per part. And what's great about these repeatable uh, durable materials is that you could easily just pick it up afterwards and then reapply it and reuse it as many times as you need for the next printed circuit board. They were also able to produce a jig. If you look on the bottom here with like the with the white text, excuse me, you can see one of the jigs that was used to in turn hold their printed circuit board during the production process. So to quickly conclude, this is a very straightforward and great application, very simple and easy to design, and also bring into your workflow. Mercury Systems was able to reduce their production costs by 95%, decrease their lead time by 85%, and TTM was also able to reduce their labor time and increase their turnaround during the production and conformal coding procedure. So one last thing I want to say, we definitely want you, so this will conclude my presentation. We definitely want you to stay tuned for future webinar content. Previous webinars that have been recorded can be found at Essentium's website. If you go to essentium.com, navigate to resources, and you can find our webinars. My previous webinar, 3D printing applications for thermoforming, has been uploaded there. So feel free to take a look, but also stay tuned for future videos. So we will continue with different topics and more exciting news. So this concludes my presentation. We'll now move on to the Q&A portion. As a reminder, please submit any questions that you have at the bottom of your screen, and I will answer them during the next 15 minutes. Thank you so much. Okay, let me take a look at the chat too. All right, excellent. Glad to see you guys have a lot. Let's see, we have a lot of visitor engagement. Just taking a look at what we have here. Okay, so first question on the ESC boots, how thin of a wall can be printed? So that's an excellent question. So a good rule of thumb for extrusion-based 3D printing, like Essentium's HSC 3D printing line, ideally we would like to stick within like roughly half the diameter of the nozzle that you're working with. So to kind of back up for a second, when you're working with extrusion-based 3D printers, you have thermoplastics that are heated up to a certain temperature and then pushed and extruded through a nozzle with a small aperture or hole at the very bottom. And so we have two what we call hosels. That's our proprietary design for our extrusion printers. Our hosels are what contain a heating element and an aperture at the end in order for precise flow and application of the thermoplastic material. So we have two hosel sizes, one with a 0.4 millimeter aperture and one with a 0.8 millimeter aperture. So ideally we like to print walls no thinner than half of that size. So if we're working with 0.4 millimeter nozzle, we wouldn't want to print smaller than the 0.2 millimeter thick wall. But also, when you're programming or creating your 3D prints, you can increase that wall thickness and have consecutive perimeters in order to thicken those walls. So you could have several, like 0.2 or 0.4 millimeter walls stacked up next to each other in order to get a stronger part. It might be kind of hard to see here, but this TPU part I have here has I think it has like three perimeters. Unfortunately, I don't think you can see each trace very well here, but if we're looking at this lip here, it does have 3 perimeters. So it depends on if you're working with a 0.4 millimeter hosel or a 0.8 millimeter hosel, And then if you take half of that diameter, that's roughly the space that we like to work in for wall thickness. Let's see. Next question. All right, very excellent question. So design considerations when printing the boots, can we avoid capillary action and coating seeping into places it can't be in? Can boots work without applying external pressure via additional fixturing? That's an excellent question. Um, so that was one that I'll have to talk with actually Mercury Systems and TTM a bit more. I'm understanding that if they did if they apply thin coats of the conformal coating and they have a properly tolerance 3D print that is pushed down firmly around each component, it's my understanding that there's enough seal that no capillary action, there will be no conformal coating that will seep in and get underneath the boot. I haven't heard of them having any capillary action issues, but that's definitely something I'm going to ask them personally, and I could definitely follow up with you if you'd like to know the answer. I'll give you guys my email address as well. Let's see, I don't have it on the slide, but I guess to start with, if you do have specific questions like that, I'll have to answer after the session. You can email sales@essentium.com, or you could even email me directly at leslie.bush@essentium.com. That is leslie.bush@essentium.com. So you can email either one of those email addresses. The question will get back to me, and then I can follow up with you as soon as possible. Okay, let's see, next question. Okay, so I have a question about, let's see, printer operator cost. So that definitely would depend from customer to customer. I wasn't privy to what Mercury's operator costs were. So unfortunately, I don't have that information. I am unsure if I'd be able to get that for you, but I could definitely see. Next, how was the white text added to that TTM jig? Very good question. So that was actually, I think that was painted on. So the 3D print had, some divots or like a recess during the print. This one here has you can see it does have some text to it. So there is a recess, like you could 3D design a recess into your model, and then in turn, take that and use it as like a way to pool and apply like some durable white paint or whatever that would kind of withstand see like chemical the chemical application for the conformal coating. Off the top of my head, I'm not sure what particular paint they used. That might have just been a display piece, but you would definitely have to choose a paint that would not degrade after multiple use cycles and multiple applications of conformal coating. Let's see. Do most customers keep the 3D printed boots on during UV cure? Let's see. That is a good question. I am actually not sure. Well, for the UV curing, um, so the UV curing procedure, that was actually material that was being masked off, um, or that was like the UV curable masking material. I'm not sure if it would be applicable because I'm sure like they would put the boots on first and then go ahead and spray the conformal coating afterwards. And the UV and some of the conformal coats don't need to be UV cured. So if I'm answering your question correctly, I believe that wouldn't be a situation that would occur for these two use cases because they're not using that UV applied or that UV sensitive masking. Feel free to message me because I want to make sure that I answer that correctly. Okay, so I have a question about trigger distance So that is related more to, I see you're one of our HSC customers. Thank you for joining us. I won't have time to really get in depth on trigger distance, but I would definitely encourage you to reach out to Essentium's service and delivery team so they can address that trigger distance question that you have specific to your machine. Or if you email sales@essentium.com, you could use that to get in contact with the service and delivery team, or submit a Zendesk ticket, and one of the service and delivery team members will address that for you. Unfortunately, I won't be able to get into that topic for today's session. And so lastly, sharing the recording link. So that will be sent out to you and all the participants as soon as we have this recorded and processed. That will definitely be shared and emailed out to you. And then it'll also be present and uploaded to, to our webinar page on the Essentium website. Okay, so with that, let me wrap it up. Thank you guys for your questions. I hope I was able to answer them as best as possible. If I didn't quite get your question right, forgive me, but we can go ahead and talk further after the session. You can email me at leslie.bush@essentium.com, and I'll make sure I can get those questions to you directly. Alrighty. Let's see, I think I have one more here. Let me read this here. Oh, I understand you now. I'm sorry. You're asking about the cure coating process in the UV oven. Okay. I will actually have to reach out to Mercury Systems. I have a weekly call with them, so I can definitely get the further steps about their particular procedure and get back to you. So thank you for your question. And if I have your name here, so I should be able to find your contact information, and I can follow up with you after today's webinar. All right. Well, thank you guys again. I'll go ahead and wrap things up. All right. Enjoy the rest of your day. Take care.